Hi everyone, so I want to just make a cleaner video of the example that we did at the end of class earlier today, which was setting up a model for worldwide CO2 emissions as a function of T years since 2000. And so the first thing to think about is, well, what would be an appropriate model for this situation? And because we're told that this CO2 emissions are growing by a constant percent, and it's this word percent here that's the qualifier that should send off some alarm bells that this would be an exponential model, would be appropriate for this situation because we have this constant percent growth. So if you're looking for a good set of steps to keep in mind, the first thing that you might want to do is consider what model would you want to use. So we shouldn't take it for granted that we're using an exponential model, but here's why. It's because of that constant percent growth in CO2 emissions. So we really don't want to go any further into the problem until we first identify what model to use. And since we're using an exponential model, this means that our model is going to look like C is equal to C0 a to the t. And then a good next step would be, well, what information are we given? And so before I, again, proceed through this, it would be useful to know what points am I given and how they might fit into this formula. So we've got one bit of information that says in 2000, emissions were 25.15. So the year 2000 is 0 years after 2000. And here, so T is 0, and we're told that the output is 25.15 billion tons. And then we have a second data point, which is given in the next bullet. We're given information about CO2 emissions worldwide in 2010. So we're told in 2010 it was 33.13 billion tons. And so this gives us a second point. In 2010, this is 10 years after 2000, so the value for T is 10, and we're told that the CO2 emissions were 33.13 billion tons. And now we need to find the values of the parameters in this model. And the way that we do this might change based on the information that we're given. But here we can see that C0 which is the initial value of CO2 emissions when T is equal to 0. And again, we're told that that is 25.15. So we know that C0 is 25.15. So let's fill that in our model. So far, we've got one out of the two parameters, namely that C0 is 25.15, and what's left to find is the growth factor A. And in order to find A, let's plug the given information into our model, the rest of the given information. So namely, we haven't used the fact that in 2010, we had 33.13 billion tons. So let me plug this into the model. So in for C goes to 33.13, and in place of T, we're now going to plug in that input of 10. And this is going to tell us that we have a 33.13, and that is equal to 25.15 times A, all raised to the power of 10. Because here, 10 years later, we know there should be 33.13 billion tons of CO2 emissions. And so now it becomes an algebraic problem where we need to solve for A. So I take this equation, 33.13 equals 25.15 A to the 10th, and I can divide both sides by 25.15. And dividing the 33.13 by 25.15, that gives us 1.3173 approximately. And on the right side of the equation, the 25.15 cancels out, and all that's left is a to the 10th power. So we want to solve for a, which is in the base of this exponent, which is being raised to the 10th power. So in order to solve for a, we can undo this operation. And the opposite of raising something to the 10th power is what we call taking the 10th root of a number. So here we can take the 10th root of 1.3173. Here we need to use a calculator. We did talk about how to use, say, a smartphone to do this calculation. But if you're stuck on how to do this, just let me know. But you can check that this should come out to 1.0279. And therefore, we've got the missing piece in our model. So this problem is asking me to construct a formula for this. So my final answer should be a complete formula. So we have C is equal to 25.15 all times A, 1.0279, all raised to the power of T. And so now we could use this model to make predictions, projections out, into the future. We can compare later data to what our model projects to see if we need to update our model and so on. But from this model, we can see that CO2 emissions seem to be growing by this percentage that we can get from the rate, so the 2.79% per year. And again, that 2.79, that comes from this rate over here, the 0.0279 converted to a percentage. So hopefully this helps. If you have some questions, we will talk about it in our next class this afternoon.